Okay, ELE 112, this is chapter 20, section 20-4, maximum power transfer theorem. And I know that you have done this before in chapter 8. It's the same. You have to do a Z Thevenin, or you have to do an R Thevenin to get the job done. With a twist. So let's take a look at the material that's here. If you read up at the top, it says maximum power when a load is connected to a circuit. Here's the load. Maximum power transfers when the load is the complex conjugate of an input circuit. So, if I may, down here, our resistance minus capacitance, or our resistance plus inductance, is a complex expression. It's not an equation, it's an expression. In the complex conjugate, this says I have a resistor and I have a capacitor. The complex conjugate of this form of an answer, and this form would come from ZT when you've got a magnitude and an angle, theta, and you convert it to rectangular. When you do that, you end up with one of these dogs or one of these down here. Now, that's your final answer for a regular ZT problem. But when they are asking you to compute the maximum power transfer, what is the load, you have to convert your final answer into a complex conjugate. Very easy, very easy. The resistance always stays. The resistance always stays. Now, the reason why you'd be in this equation is because you ended up with a ZT that has capacitance and resistance. And the reason you would be over here is you ended up with a resistance and an X sub L as your ZT. So what we do is we flip the sign and we change the component. Isn't that sweet? So we flip the sign and change the component. That's how you derive the maximum power. You can see up here they're trying to show you this. The complex conjugate of R minus JX sub C is R plus JX sub L, where the resistance and the reactance are equal in magnitude. So if this is 10K, it was 10K up here. If this is 1K, it's 1K down here. You don't have to do a whole lot. So the Thevenin equivalent of a circuit, to get maximum power, you have to provide the complex conjugate as its solution to be able to deliver the maximum power from the circuit to the load. This gives you a power factor of 1, making it all resistive. Power factor equals 1 means that all the capacitance and inductance is nullified, or at resonance, if you will, and it disappears, and all you've got is a load. Taking this circuit into account here in the once again, we're looking at this circuit and we're calculating at 10, 30, 50, 80, and 100 kilohertz. We're looking for the spot where these two components are the complex conjugate. Two components here to cancel, they have to be equal. Next slide here, you can see that they've gone ahead at multiple frequencies. Let's freeze that puppy and get it out of there. At 10K, at 30K, at 50K, and at 80K, they went through the process of calculating X sub L and X sub C. Now, the magnitude of the total impedance, if you add and subtract all of these, this is their Mickey Mouse equation that they use in the book. You could have taken it as the resistance at 0 plus the resistance at 0 plus the inductor at angle 90 plus the capacitor at angle minus 90. You would have come up with this. That says that we have nothing but resistance at this point. Okay, we have nothing but resistance at this point in the circuit, and that's the magnitude of it. And you can find that the current is 6.54 milliamps through that circuit. Well, to calculate the power, you need current and the load, and that gives you 428 microwatts, a very, very small amount of these two components. Okay, so computing at 30 kilohertz, which is getting bigger and potentially approaching resonance, X sub C is 531, X sub L gets cranked out as 189 ohms, and the total magnitude of the resistance is 343, which gives you a larger current. It's bigger. It's bigger. It also generates a larger power. It also generates a larger power. Now, I'm not at resonance here. I don't have X sub L and X sub C canceling in either of these. You see, they're not the same value. For the opposite, that just hasn't happened yet until we hit 50 kilohertz. Now, at 50 kilohertz, magic happens, and the two components are essentially the same value. If you remember the plot for capacitance and the plot for in X sub L, there is only one spot, the resonance spot, and we just found it right here. Now, they're very close, and when you calculate the magnitude of the impedance and the current, which has surged beyond the value of what we've seen in the first two calculations, we get a 2.4 watt, a huge spike in the power that's delivered to the load. Now, if we go further, you go, oh wow, the power is just getting bigger and bigger. If we go further, look what happens to X sub L and X sub C, because we're out here in this range with the higher frequency where the yellow bubble is, and the impedances, they migrate away from each other, again, shrinking the impedance, shrinking the power, and produces 10.8 milliwatts, which is a lot smaller than 2.4 watts, right? Okay. Again, at 100 kilohertz, things degrade even further than what we've seen, shrinking the power as shown on the screen. To the right, you see X sub L here is bigger than X sub C. So, that being said, here's what actually happens. Okay, here's what actually happens. If you plot this on the screen that you see here, and you do power versus frequency, you see that at 50 kilohertz to the left, the capacitor, and to the right, the inductor is dominating. The values shrink, and the power, P max, occurs when the capacitor and the inductor are equal. So, for max power, X sub L must equal X sub C, and they are opposites of each other, obviously, with respect to frequency. So, if you have an R plus J X sub L, the solution to get maximum power is J x sub C with a minus sign, not a plus sign. With the minus, this is a minus sign, okay? So make sure you got that right. Now, let's take a look at a few working problems, shall we? Here's a simple series circuit with a load plugged in, and it wants to know what value should this be? What value should that be? It doesn't want to know what the actual value of the capacitor is. Unless you're given F, you can't do that. But it wants to know, I've got 10 plus 4K. I've got 10 plus 4K. How do I get maximum power out there? Well, I climb in here and I peak. Now, I don't really have to peak very much because, well, this circuit is real simple. We take the power supply, we short it, okay? So we got a shorted power supply. And we look in with our eyeball right here, R and X sub L. Well, the solution, instead of R plus X sub L, the solution is Z Thevenin is equal to R minus J X sub C. Now, I don't want to say Z Thevenin. It's not really Z Thevenin. It's the load. The load needs to mimic R minus J X sub C to cancel out X sub L and X sub C, leaving just R. And what we do know is that when we have just R and R, whether it's 1K and 1K or 2K and 2K, we get maximum power delivered here when that situation occurs. Problem number 2, a little different. We have a current source in there. We have to Thevenize to find out what the load needs to be. You're always going to Thevenize to find out what the load needs to be. So you put your eyeball here and you look in and you open. Here we are. We open the back end. So all we see is this series link here of 10K in series with a 5K inductor, ohms and ohms. And so to solve this, to have maximum power delivered, we need to have the complex conjugate of 10K plus 5KJ. You getting the hang of this? Here's the last problem. Looks a little big until you short the power supply right here. We have to short the power supply, and now we end up with a parallel branch in series with a resistor. So we set up our Z Thevenin here, we look in with our eyeball, and we see a parallel branch. So we immediately go and hack away, come up with a Z total for that branch, plug it back into here, and when we add that to 50 at 0, which is done down here, you end up with 50 plus 40J. So if you want to match your load, you have to match the Thevenin equivalent, looking in with your source shorted if it's a power supply and open if it's a current source.